Okay, we are continuing to move out throughout the solar system. We're to our last two planets. We're going to do Uranus and Neptune both in this same video. And again, another reminder that I am just skimming the surface of the information on the planets, so be sure to read your textbook chapters after each video and any supplemental videos I post for you to watch on YouTube. Uranus is the first planet we encounter that we haven't known about for 1,000 years. It isn't visible to the naked eye. You can go out and see Mercury and Venus, or Mars and Jupiter or Saturn, any place with dark sky and a clear horizon, various times of the year. You don't need a telescope to see them. We talked about the fact very early in the class that the reason the number 7 is often associated with the skies and the heavens is because there are 7 interesting things you can see in the sky: Mercury and Venus, Mars, Jupiter, Saturn, and the sun and moon. But Uranus is too dim to see without the use of a telescope. It wasn't discovered until 1781 by an astronomer named William Herschel. Through Herschel's telescope with just like a tiny bluish green circle. We have only explored Uranus up close once. That was at the Voyager 2 spacecraft in the 1980s. And up close it looks like a big greenish blue circle. There's not a whole lot going on the visually with Uranus to talk about. Like Jupiter and Saturn, its atmosphere is largely hydrogen gas. Something like 83% hydrogen, 15% helium, and the rest elements like methane. I think there's a little water vapor and stuff in there too. But like Jupiter and Saturn, its atmosphere is very, very thick. And until very, very recently, Uranus and Neptune were both categorized as Jovian gas giant planets like Jupiter and Saturn. Also present in the atmosphere, ices, just like we find in the upper atmosphere of the other Jovian planets: ammonia ice, water ice, methane ices, things like that floating in the atmosphere, much the way little crystals of ice, water ice, float in the Earth's atmosphere. Now that we're out another 10 AU or so from the Sun, further than Saturn, the temperature is about 50 degrees colder than it was at Saturn. So at the tops of Uranus's cloud, the temperature is about 350 degrees below 0 Fahrenheit. It does not receive much sunlight, so there's not a whole lot of heat energy driving the activity of the clouds the way we saw on Jupiter and Saturn. There is some activity in the clouds of Uranus that reveals itself in the infrared. These are some infrared photos, and you do see that there are actually these alternating high pressure, low pressure belts and zones in the atmosphere, and we do see some clouds in the atmosphere. There's actually some indication that when we flew by Uranus with the Voyager spacecraft back in, I think Voyager flew past Uranus in the early 80s, we maybe just caught it on a bad couple of years when there wasn't a whole lot of activity in the atmosphere, and it seems like maybe the atmosphere is maybe a little more active now than it was then. But regardless, certainly not as active as Jupiter and Saturn, certainly not as much to see. You will notice in this infrared photo that we can see the rings of Uranus. And you will also notice that the north pole of Uranus is here, not at the top. This is not just a weirdly tilted photograph. This is a weirdly tilted planet. Uranus is tilted on its axis almost all the way over. It's tilted 80-some degrees from the plane of its orbit. The Earth is tilted 20-some degrees. That's why we have seasons, because sometimes our pole is pointed kind of towards the sun. Sometimes Uranus's pole is pointed almost directly towards the sun, which is unusual in the solar system. Most of the orbits and the rotations of the planets in the solar system are fairly up and down. Uranus is way over on its side, and the question is why? What could have caused such a thing? Our best guess, it was some sort of collision early in the history of Uranus's formation that actually tipped the whole planet over on its side. Maybe the collision was something as large as the Earth or Mars, some large object in the solar system that doesn't exist anymore. It got swallowed by Uranus 4 billion years ago. Uranus does have rings like the other Jovian planets. Again, they're not as grand as Saturn's rings, but all the Jovian planets has rings. It has a couple of moons. You can see a few of its moons, and there's one right there in this photograph. We're not going to talk much about Uranus's moons, but it's worth noting that all the Jovian planets have dozens of moons, and it's a pretty standard feature of these Jovian planets. Again, in this false color image, you can see some structure in the cloud tops when you look in the infrared and in other wavelengths. Here's one of Uranus's moons, 27 last I checked. These numbers change sometimes. I don't think we've discovered any moons of Uranus for a very, very long time. This is Ariel, one of its largest moons, and it has an appearance similar to a lot of the moons in the outer solar system, a surface that's a combination of rock and ice, some craters, but not as many as, say, Mercury or the moon. Instead, these kind of long, cracky, groovy, icy structures that we'll talk about in the context of talking about moons in general, and I'll save that for a separate lecture. The thing that makes Uranus and Neptune different from Jupiter and Saturn is their internal structure. I said that we used to use the blanket term for Jovian planets as gas giants. The idea being that they're mostly gaseous until you get to this liquid metal center and then finally maybe a rocky or icy core. Uranus and Neptune's internal structure seems to be a little different. They are hydrogen gas pretty deep into the interior of the planet until you get to a region that is, we think, mostly ices. Water ice, ammonia ice, methane ice. So the bulk of the planet is denser than hydrogen gas, denser than liquid hydrogen. So we think the interior of both Uranus and Neptune is a thick mantle of ice. And then maybe in the very, very core, a tiny rocky or even an icy core, maybe a little bigger than these. So this is an Earth to scale to Uranus and Neptune. The cores of these planets probably maybe the size of Mars or smaller, maybe the size of Mercury or our moon. So the new term that is sometimes used to refer to Uranus and Neptune collectively is ice giants instead of gas giants, because we think their interior is largely ice once you get down past the first 20% or so, which is just atmosphere like the other gas giants. This is Neptune. Neptune also you can't see with the naked eye. It's even further away from the sun than Uranus. The discovery of Neptune is really, really interesting in the history of science. It is the first planet whose existence was predicted before it was observed. After we discovered Uranus, we started plotting its orbit through space and calculating the force of the sun on Uranus and how it should orbit around the sun. And what we found is that our calculations were always a little bit off. If you use Newton's law of gravity and Newton's laws of motion to predict where Uranus should be month after month, year after year, those predictions were always wrong. When we went and looked at Uranus, it was always not quite in the place where astronomers predicted that it should be. Now, if science works the way that you were told it worked in middle school, when you have an experiment that doesn't work, the thing you're supposed to do is to change your hypothesis, right? Well, we didn't throw away Newton's laws of motion when we found out Uranus wasn't moving the right way. What we said was, well, maybe we're missing something when we compute the trajectory of Uranus. And a scientist by the name of Leverrier said maybe what we're missing is that there's some other gravitational pull pulling on Uranus, pulling it away from the sun to cause it to not travel exactly the path that we expected. Leverrier actually calculated where that object would have to be in order to be slightly tugging Uranus off of its predicted path. And these differences were very, very small, but measurable. And Leverrier contacted some astronomers and said, you should point your telescope kind of over there and see if you find a planet. And in 1846, a guy named Johann Galle discovered Neptune, right there where Leverrier predicted it would be. So they're jointly discovered with the discovery of Neptune. When I think of Neptune's discovery, I usually think of Leverrier, but he wasn't the actual person who looked through the telescope and found it there. Neptune looks similar to Uranus, kind of this bluish color that is from the methane in the atmosphere largely, but a much more dynamic atmosphere, much more going on in Neptune's atmosphere than in the atmosphere of Uranus. We've only looked at Neptune up close really once. That was with the Voyager 2 spacecraft. I think flew by Neptune in the late 1980s. And what we find is some persistent storm systems, much like Jupiter's Great Red Spot. Neptune has a Great Dark Spot, which is a persistent cyclonic storm system in the atmosphere of Neptune that lasts for decades, at least, at a time. But we also see high clouds in the atmosphere, and they're very fast moving. These are clouds of ammonia, hydrogen sulfide, things like that. They're in the upper layers of the atmosphere, and they move very, very fast. One of the interesting things about Neptune is we have detected the highest speed winds on Neptune that we have detected on any planet. There have been wind speeds measured up to 600 meters per second. That's more than 1,000, actually 1,300 miles per hour. That is unexpected. And the reason it's unexpected is, remember, what drives the activity of an atmosphere, at least in the inner part of the solar system, is the heat from the sun. The sun shines on the Earth, it heats up different parts of the Earth differently, it makes the air move around, it causes wind and low pressure and high pressure systems and storms. There is not a whole lot of sunlight falling on the top of the atmosphere in Neptune. The temperature on Neptune is almost 400 degrees below 0 Fahrenheit. It doesn't make any sense if the driving source of energy is heat from the sun, that Neptune would have a more active atmosphere than Uranus would, because Neptune is colder than Uranus. This suggests that whatever the driving force is behind this heat in the atmosphere, that some of it is coming from the inside. And there are various ideas for what that might be, and the reasons why Neptune might be producing more internal heat than Uranus does. Some of the ideas have to do with the magnetic field. Some of the ideas are, well, I'm not even going to talk about them in this video because I'm going to assign an article for you guys to read that explores some of the differences between Uranus and Neptune and some of the possible explanations for why these two planets might be very different from one another. So stay tuned for that outside of the videos. So here's a close-up picture of the tops of the clouds of Neptune, showing these high, fast-moving clouds in the atmosphere, and again, moving at speeds far in excess of any wind speed we've ever measured on the Earth. We consider a 200 mile an hour, 250 mile an hour hurricane or tornado the highest imaginable winds that you can have. Well, here we're talking about wind speeds that are 5 times faster than that, despite the atmosphere being 350, 400 degrees below 0. It's weird, and it doesn't make a lot of sense. So there are things that we still need to learn and figure out about these outer planets that we don't know yet. Yeah, so I'm going to let you guys do a little research on your own to answer the question of why maybe that this is true of the planet Neptune. Neptune's got about 13 moons, if you don't count the particles in the rings. I don't think I have a picture of Neptune's rings because they're really hard to photograph. Neptune's rings are actually partial. Some of them are sort of disconnected arcs that don't go all the way around the planet. So it does have rings, but they're kind of paltry rings that don't actually circle the planet all the way. So it's hard to get a good photograph of them. But it does have a bunch of moons. This is Neptune's most interesting moon. I don't know why my green screen is looking so bad today. Oh, that helped. Triton is the largest moon of Neptune. It's way bigger than all the other moons of Neptune. All the other moons of Neptune are tiny. That's the second biggest moon of Neptune. It's called Proteus. So there's not much point talking about the other 10 moons. 10, 11 moons. Triton is the interesting one, and Triton is interesting for a bunch of reasons. First of all, it looks interesting. It looks cool. There's like a different kind of terrain here than there is here, and there are these weird little black stains on the surface that look a little bit like the volcanoes on Io looked. We think that these black stains are actually geysers of liquid nitrogen. We had to invent a whole new word to describe these objects in the outer solar system. We call them cryovolcanoes. So on Earth we have geysers, right? We have these places where water underground is heated to boiling and it bursts out of the ground. There's like Old Faithful in Yellowstone, right? I was just this past early this summer, I went to Iceland. And Iceland, you might know, Iceland has a lot of volcanic activity. The whole country is heated by geothermal power plants. That's how they make their electricity, because the heat from inside the earth is so accessible there. Basically the mid-Atlantic trench runs right through Iceland. And we went to see some geysers. That every 2 or 3 minutes the water boils into steam and the pressure heats up enough that it bursts out of the ground. Well, this is the same thing happening hundreds of degrees colder, where frozen nitrogen is turning into liquid nitrogen, and that is heated up into a gas, and that bursts from the surface in a geyser that, instead of being the boiling point of water, is the boiling point of nitrogen, which is 200 and some degrees below 0 Fahrenheit. So the surface of Triton is mostly ice. Frozen nitrogen, which is something you've probably never seen before. You might have seen liquid nitrogen, but not frozen nitrogen. Frozen CO2, which maybe you have seen before. We call that dry ice here on Earth. And regular old H2O water ice. So about half solid nitrogen and the rest a mixture of frozen CO2 and frozen water. The whole object has a very low density. It's much less dense than rocks. So we think the whole moon of Triton is a mixture of rock and ice once you get down below the surface. Its size, its density, and its physical appearance are all very similar to Pluto. I almost said the planet Pluto, but we don't consider Pluto a planet anymore. And one of the reasons is that Pluto has way more in common with icy moons like Triton than it does with terrestrial planets like Mercury, Venus, Earth, and Mars. In fact, the orbit of Triton around Neptune is the wrong way. I said that everything in the solar system in an earlier video, everything in the solar system goes around the sun in the same direction. The planets all go around in the same direction. The moons of the planets go around their planets in the same direction. The planets almost all spin on their axis in the same direction, with a couple of exceptions. Uranus being one of them, being on its side. But everything in the solar system formed from the same spinning cloud of gas and dust, so it all goes around in the same direction. Why would Triton go around Neptune in the wrong way? We think because Triton did not form around Neptune. Triton was an object that used to be a separate object from Neptune and got captured by Neptune's gravity into an orbit, which is why it's not going the way that everything is going when the solar system formed. Because Triton is not an original moon of Neptune. It didn't form there. We think that Triton was an object in the Kuiper Belt. I think we've talked about the Kuiper Belt before. The Kuiper Belt is this region beyond Neptune where there's all this kind of leftover junk from the formation of the solar system. There are bits of rock and ice the size of grains of sand and gravel and ice cubes, up to the size of cars and houses, up to the size of Pluto. We no longer consider Pluto a planet. We consider Pluto one of the largest and closest Kuiper Belt objects. And there are many other objects out there like Pluto, some of which we'll talk about when we talk about Pluto. So Triton used to be a Pluto with its own orbit around the sun. That orbit was close enough to Neptune that Neptune snatched it up, and now Triton orbits around Neptune, we think. So Triton and Pluto have way more in common than Pluto and any of the other planets. So when we talk about these trans-Neptunian objects out beyond the orbit of Neptune, we'll maybe revisit Triton a little bit, but also talk about the similarities between Triton, Pluto, Pluto's moon Charon, and all the other weird little junk out there in the Kuiper Belt. Yeah, I think that's all I'm going to say about Uranus and Neptune. That was a really, really quick 20-minute video. So, again, read the book chapters about these objects. I'm going to post an article about the interiors of Uranus and Neptune and how we think they might have been shaped in similar ways early in their formation by collisions in the outer part of the solar system that were way more frequent and violent billions of years ago than they are now.